All right, in this video, we're going to go through the Unit 6 practice test to kind of see the stuff you need to know for your Unit 6 assessment. All right, so our first skill is the squeeze theorem. All right, so in this problem, we actually have to use the whole squeeze theorem to our advantage in order to figure out this limit. We can't figure out this limit by just plugging in 0 because it's this cosine of infinity type thing, which doesn't quite make sense. So we want to figure out what this limit's going to be. So the first thing we're going to say is cosine is always smaller than 1 and less than negative 1. So if I have x cubed cosine of 1 over x, that always has to be less than or equal to just x cubed if I replace the cosine with a 1. And always has to be bigger than x cubed if I replace the cosine with a negative 1, right? This is always smaller than cosine. This is always bigger than cosine. All right, so now the squeeze theorem says, all right, I have these kind of bounding functions, one function that's always bigger and one function that's always smaller. So the next thing to do is look at their limits. I'm going to look at their limits at the same limit I actually care about. So I'm going to limit as x approaches 0 of negative x cubed. All right, negative x cubed is just a polynomial. I could just plug in 0 and I get negative 0 cubed, which is 0. So my bottom bounding function goes to 0 as x goes to 0. My other one, just x cubed, again, it's just a polynomial, so I can just plug in the number. I also get 0. That's exactly what I want in the squeeze theorem. I want a function below and a function above that are kind of squeezing together to the same number. So now I can say, by the squeeze theorem, that's an E. So by the squeeze theorem, I know these two things are happening. I can say my limit of the function I care about equals 0. All right, so this is the squeeze theorem. You have to identify the lower function and the higher function. You need to show that they both have the same limit, and then by the squeeze theorem, the middle thing has to have the same limit. All right, so here's question 2 of the squeeze theorem. This is more the way it's asked on the AP test. All right, something like they give you a g function, they give you an h function, and they say we're trying to figure out some function about f, which is in between those two. All right, we want to find the limit as x approaches 1. So from what we just saw with the squeeze theorem is if these bounding functions, g and h, are the same number, then f has to also be the same number. So we have to check the limit as x approaches 1 of g of x, which is plugging in 1 for x. So that's going to be sine of pi over 2 plus 4. Sine of pi over 2, that's going straight up. That's when sine is 1. And I get 5. Right, now I also have to check the limit as x approaches 1 of h of x. And make sure you check both. I can't just say the answer is 5 because h has to be the same value. So that's going to be plugging in 1. This. So I'm going to get negative 1/4 plus 3/4. And just because I know I'm going to have to get a common denominator, I'm going to turn 9 over 2 into 18 over 4. 2 plus 18 is 20. And 20 divided by 4 is 5. So I do get the same number as these. So by the squeeze theorem, f is in the middle of these two that are both 5. So the limit as x approaches 1 of f of x also has to be 5. Right? But all right, to get full credit for this problem, I have to see you evaluate the limits of the bounding functions and say by the squeeze theorem you're getting the same value. All right, our next skill is about taking the derivative of trigonometric functions. So we have those 12 different derivatives that could come up for our 6 trig functions and also the 6 inverse trig functions. We also have to make sure we know the product rule, the quotient rule, the power rule, the chain rule, all that stuff. All right, all that stuff is combining together. So the first one, let me just zoom in a bit. Cotangent of x, all right, that's just a trig function. I just know its derivative is negative cosecant squared. All right, that's literally just like a flashcard thing. Nothing fancy happening there. You just have to know the derivative of cotangent is negative cosecant squared. All right, for g prime of x, I'm looking at this thing that is a fraction, so I have to do the quotient rule. So quotient rule is low times d high, so the derivative of x squared is 2x, minus high x squared, d low, the derivative of cosine is negative sine, so I'm going to put the sine, and the negative sign is going to turn that to a positive, and that's all over low, which is the original bottom squared. And I'm not too worried about you simplifying. I'm just making sure you know your derivative rules, you know the trig derivatives, you remember the quotient rule. All right, that's fine for your final answer. Right, h of x secant of the square root of x. This is a chain rule problem because we have these parentheses. So what we're going to do is h prime of x. We do the outside function first. So the derivative of secant is secant times tangent. And remember, when you're doing the chain rule, the thing in the parentheses stays the same in the first step. So both of these, all right, secant's kind of the weird one. We get these two things, but both of those are going to have a square root of x in it. So I kind of took care of the secant part. And now the next thing I do is multiply by the derivative of the square root of x. You could do this by changing this to x to the 1/2 and doing the power rule. The square root of x comes up so often, it might just be helpful to remember the square root, or sorry, the derivative is 1/2 square root of x. Just saves you a lot of time. It comes up so often. That might be also worth having on a flashcard. And notice I only have to do this once because it's just this one inside thing. I'm not multiplying by both of these for the chain rule, even though there's two parentheses. I'm doing the chain rule to the original function, so I just have this one square root of x, which turns into its derivative. Our next one, tan squared of x. This one tends to give people trouble because the notation makes it look like tangent to the outside function, but this is technically a shorthand of this. I'm going to use this notation just so we don't have these extra parentheses and it's kind of a little bit simpler to write. But if you write it this way, you can see this 2's on the outside. So I'm going to take the derivative. The outside function for the chain rule is that 2. So I bring the 2 down, keep the inside the same, and subtract 1 from the exponent, so now it's tan to the first. Then I multiply by the derivative of the inside. The derivative tangent is secant squared. That's my final answer is 2 tangent secant squared. All right, and the last two, x cubed sine of x. All right, these ones look really simple, but it's a little bit more complicated because it's x cubed times sine of x. So I have to do the product rule. The product rule says I'm going to keep the first function the same, so that's going to be x cubed. I'm going to multiply by the derivative of the other function. The derivative of sine is cosine. Then I'm going to add. I'm just going to switch it around. Now I'm going to keep the second function the same and multiply that by the derivative of the first function. Again, no simplifying necessary for this test. Just want to make sure you remember the product rule, you know your sine, cosine derivatives. All right, and lastly, d prime of x. All right, there's cosecant of 4x. So again, it's a chain rule because there's that 4x on the inside. So the first thing I need to do is take the derivative of cosecant, which is negative cosecant times cotangent. And again, just like with secant, it kind of creates these two parentheses, but this inside 4x goes into both of those. And I multiply by the derivative of the inside here, which is just 4. All right, so those are our trig derivatives. All right, just making sure you remember what the original 6 are, and then not forgetting our original rules like the quotient rule, the chain rule we did 3 times, and we did the product rule. All right, our next skill is about L'Hopital's rule. So L'Hopital's rule says if I get 0 over 0 or infinity over infinity for a limit, then I can do derivatives to simplify the limit. All right, in order to get full credit here, we got to do it like the AP test wants us to do. So when I go to this first problem, oops, let me zoom out just a little bit more. There we go. All right, when I go to this first problem, well, the first thing I would want to do is try to plug in 3. It doesn't work, so I go to the side and I say the limit of the top is a polynomial, so I just plug in the number and I get 0. The limit of the bottom, I plug in 3, I get 0. All right, so I show that I get 0 for the top and bottom. So now I can go over here and say by L'Hopital's rule. I put this little L'(h) for L'Hopital's rule above your equal sign to show what you're doing. And the L'Hopital rule says I take the derivative of the top, which is just 2x, over the derivative of the bottom, which is just 1. And now I can try to reevaluate this limit. This one's simple. I just plug in 3, and I get 6. All right, so to get full credit on this one, I know it's tedious, but this is the way you're going to have to do it in the AP test. We might as well learn it now. All right, show the limits are 0 on the side, and then show that you're doing L'Hopital's rule, and then evaluate the new limit. right, so in question 2, all right, to the side, limit as x approaches 0 of sine of x minus x. That's sine of 0 minus 0. Sine of 0 is 0, and we get 0. All right, limit as x approaches 0 of x squared. We plug in 0, we get 0. So we can do L'Hopital's rule. Again, L'Hopital's rule says I keep the limit the same. Oops. But now I'm going to take the derivative of the top, which can be cosine of x minus 1, over the derivative of the bottom, which is 2x. And now I just retry to do this limit, in this case. Put it in 0. Cosine of 0 is 1. Actually get 0 on the top and 0 on the bottom again. So now I'm going to have to go and do L'Hopital's rule again. So I'm going to show these limits. All right. Just doing it real quick. Putting in 0. I get 0, 0 again. So now I can do L'Hopital's rule again. Right. The derivative of cosine of x is negative sine of x. Derivative of 1 is 0, so it goes away. Derivative of 2x is 2. And now I can just plug in 0. Sine of 0 is 0, so I get 0 over 2. Negative 0 over 2 doesn't matter. I get 0 as my final answer. At this one, just be careful. Sometimes you have to do L'Hopital's rule more than once. And yeah, looks good. All right, question 3. Again, first thing I'm going to do is do the individual limits. All right, for the top, I plug in 1, and I get 6. For the bottom, I plug in 1, I get 7. Not 0 over 0, not infinity over infinity. My answer is just 6 over 7. All right, nothing bad happens. I can just take the limit by plugging it in. All right, this question's here just to make sure you just don't do L'Hopital's rule every single time you see a limit with a fraction. All right, make sure you're actually checking the individual limits. Make sure they're not 0. All right, last one. Now we have the limit at infinity. All right, so we're going to show our individual limits. If I put infinity into this polynomial, 3x squared is just going to get really big, and it goes to infinity. On the bottom, same thing happens. All right, it doesn't really matter what happens with the smaller x's, just the biggest x, and I put in infinity, I'm going to get these really big numbers, infinity. So I can do L'Hopital's rule. All right, just the power rule a few times. And I notice I still can't really just plug in infinity, so I'm going to do L'Hopital's rule again. And all these, you're just putting in a really big number, you're going to get a really big number out. So I can do L'Hopital's rule again. Right. And the fraction simplifies to just 6 over 4. And it doesn't matter that I'm plugging in really big x's because no x's to plug in. I'm just going to get 6 over 4 no matter what. So my answer is just 6 over 4, which simplifies to 3/2. Right. If you know your algebra really well, you actually do this problem without L'Hopital's rule. When these exponents match up, you just look at the coefficients. That's not something you have to do. All right, now we have L'Hopital's rule. You don't need to know that algebra skill. You can just do L'Hopital's rule to get your answer. All right, our next skill has to do with derivatives of inverses. So here we have to know our inverse trig derivatives as well as how inverses work with derivatives. So this first part here is just making sure we know our inverse trig derivatives. All right, so here we have arctangent of x. This is just, again, a flashcard thing. Knowing the derivative of arctangent is 1 over 1 plus x squared. All right, so again, nothing fancy happening there other than some stuff we did earlier, but right now it's just to the point where you should have those memorized. Next one, g prime of x. First of all, any constant in front of something you're taking the derivative of can just stay. So the 4 is just going to hang out at the front for right now. All right, and then we have x cubed inside of arc cosine of x. This is a chain rule. So the first thing I'm going to do is the derivative of arc cosine, which is negative 1 over the square root of 1 minus x squared. But the x that's in that normal thing is whatever's in the parentheses. X cubed squared. All right, so whatever's in the parentheses is going to go there, squared in the formula for arc cosine. And then again, because there's something on the inside, we have to multiply this by its derivative, 3x squared. All And this one I'm actually going to just simplify a little bit. I'd be fine if you left it like this, but this 4 is going to go up here. This 3 is going to go up here. It's going to give me negative 12 x squared over the square root of 1 minus x to the 6th. I remember when you double exponent, you multiply them to get x to the 6th. So this is the way you'd probably see it on a multiple choice question. And then question 2 is just more generally about inverse functions and how they work. We have our function f given to us, and we know a point on f. We want to find the value of its derivative of its inverse. All right, so when we're doing these, I think it's really helpful to write down your x value, your original function, and your original function's derivative, and then also your inverse, the same type of table. So right away, they tell me the point 0, 1 is on my graph of f. So 0 for x and 1 for y is my input and output for my original function, which means when I switch to my inverse, all that happens is x and y flip. So the 0 now becomes the y value, and this 1 becomes the x value. All right, so that switch is the one that happens with the points, and then we know the derivatives are related because they're reciprocal. So if we can figure out this f prime of x, we can figure out its inverse by just making it reciprocal. So how do we figure out f prime of x? We have the function given to us. We can take f prime of x, negative 6x squared minus 3, and we're putting in our x value that we care about for our original function, 0. So f prime of 0 is negative 3. All right, so we get negative 3 for my original function at 0. When I switch to my inverse at 1, then all I do is take the reciprocal of this value, and the reciprocal of negative 3 is negative 1/3. All right, so my final answer is, I'll actually write it separately, f inverse prime of x, not x, of 1 is negative 1/3. All right, so it's just really important for these inverse ones that you're just keeping track of your original function, your point, and your derivative, and then you flip the point, reciprocal the derivative to get your inverse values. All right, next skill is antiderivatives involving our trigonometric functions. All right, so some of these are just kind of memorization. Secant tangent looks like a pretty hard one, but we just have this thing that we know the derivative of secant is secant tangent, so the antiderivative of secant tangent, I don't need that anymore, is just secant. And you can always double check, if I take the derivative of secant, I get secant tangent, so I'm going backwards to get that thing. All right, so this one's just basically a flashcard thing again. This one's more complicated. I had this fraction and cosine cubed. Again, I always like to think that when I have that little notation, cosine cubed, that's cosine of x cubed. And now I can see those parentheses, and generally whenever we have parentheses in a thing we're trying to find the antiderivative, that's going to be our u. So our u is going to be cosine of x, which means du is negative sine of dx, which means du over negative sine of x is equal to dx. Right. So now our more complicated integral becomes sine of x over u cubed times du over negative sine of x. And again, you know you've done u substitution right if the things with the x's cancel out. And so now I'm just going to kind of write it down here. And this is the integral of negative 1 over u cubed du. How do we take the integral of this? Well, whenever we're trying to do something with powers, we just want to rewrite it as a negative exponent. And then we're going to add 1 to the exponent and divide by the new exponent. And then we're going to replace u. And this one, the negatives cancel. And also, I just don't like having negative numbers in my final answer. So it's 1 over 2 cosine of x squared. And that's my final antiderivative using u substitution. This next one looks really complicated. Right? It's a square root. You can't just rewrite it as a power of x or something like that. But this follows the same pattern as one of our inverse trig derivatives. So this one we're going to rewrite as 1 over the square root 1 minus 2x squared dx. So for all those inverse trig derivatives, if we rewrite them as kind of this thing being squared, that's going to be important for our thing. This one follows the arcsine formula, and is normally arcsine of u is that, a is that, it's u over a, so it's 2x over 1 plus c. All right, so that's the kind of general formula, but if our u has an extra number in front of it, we have to divide by that, so it's going to put an extra 1/2 in front of that. All right, so these are, when we just have those like formulas memorized for your inverse trig derivatives, this 2x and 1, that goes on the inside, and then whenever there's a number in front of the x, you have to do an extra little division there. All right, this next one is probably one of the harder problems to see. The thing you might try to do at first for this one is make u equal t squared, du equals 2t, dt, du equals 2 over t. All right, if you did all this, which is like good if you're thinking about that, you end up getting this integral 1/2 at the front. Right. But you still have sine times cosine. We don't have a normal antiderivative for sine times cosine. All right, there's a ways you could do it, but it'd just be like an extra thing. So actually we don't want to make u just t squared, so we need to figure out something else to make u. And the thing we're going to do for this one is make u sine of t squared, this whole thing. Why do I know this is going to work? When I take the derivative of sine, it's going to turn into cosine, and the chain rule is also going to give me like this extra t. So when you have sine and cosine in the same problem, generally you're going to make u one of them. I do the chain rule, cosine of t squared times 2t dt, divide All right, so now my problem is going to become this. All right, I haven't done anything with this t yet. Sine of t squared is u. I haven't done anything with cosine of t squared yet. But dt is du over cosine of t squared times 2t. All right, so now we cancel out what we can. Cosine of t squared completely cancels out. That t cancels out with that. And we get, oops. This 2 out here, I'm just going to put it at the front. So we have this 1/2. All right, the 2 is on the denominator, so it's going to be 1/2 u du. I would take the derivative of u. We add 1 to the exponent and divide by the new exponent. And then we replace u with sine of t squared. All right, so this one's on here just as like a heads up that even though we almost always make u the thing in the parentheses, sometimes it doesn't work. Sometimes you have to try other things. All right, so this one you can make u sine of t squared, that whole thing, and then everything else cancels out. You could actually get away with this one of making u cosine of t squared, and your answer will look a little bit different. There'd be like a negative sign and some slightly different things. All right, but when sine and cosine are together in a problem, generally u is going to be one of those, like we saw up here. U is cosine of x. The next skill is definite integrals, all right, with our trig functions. And this one's just making sure that you know how to plug numbers into your trig functions. All right, same thing we're going to do in the previous one. The first thing we need to do is figure out the antiderivative of this. So the antiderivative of cosine is positive sine. So I take the derivative of sine, I get positive cosine. And I want to evaluate that from 0 to 2 pi. All right, so we're doing this fundamental theorem. We plug in the top value first. Then we subtract when we plug in the bottom value. Now we just need to figure out what these are. If we have our unit circle, we start here. 2 pi is all the way around the unit circle, so at this point, and sine is the y value of this point, which is 0. Sine of 0, we haven't moved at all, so we're still at this point. That's 0. 0 minus 0 is 0. Right, so this whole answer is just 0. I think I'm kind of checking that A, you just know the fundamental theorem. You take the antiderivative and then plug in the bounds. And then B, I'm also making sure that you know how to evaluate your trig functions. That's going to be the same thing we do here. the antiderivatives first. I'm going to take the antiderivative of sine of 4x. You could do full u substitution, but we saw a little shortcut. Sine is going to turn into negative cosine when we take an antiderivative 4x. And then I set the divide by this number. That's all that really happens when you're doing the just a simple number in the parentheses. You just basically divide by it. You're undoing the chain rule. We're evaluating that from 0 to pi over 4. So now the first thing we're going to do is plug in pi over 4. And plug in 0. Cosine. All right, so these two negatives here cancel to give me a positive. Inside of this one's 0, the inside of this one's pi. If I think about my unit circle, we know 0 is the obvious one, just going to the right. Pi is half of the circle, so that's going to the left. So cosine of pi is -1 because it's the x value there. Cosine of 0 is just going to the right. That's +1. This is +1/4 plus 1/4 is 2/4, which is 1/2. All right, so for this problem, we get 1/2 is our final answer. So again, just making sure you can take a basic trig antiderivative, and then you remember how to use the fundamental theorem to figure out the final answer. And our last skill is the one that probably takes just as long as all the other ones combined. It is the related rates problems. So there's kind of two more basic ones with shapes and the one like full word problem one. All right, this one has a rectangle, has a length of 4 inches and a width of 2 inches, whose sides are changing. The length is increasing by a certain amount. What is the rate of change of the area? All right, so we know the area of a rectangle is base times height. I guess I used length times width, so it's used length times width. Because there's the letters they're giving us. Length times width. Now we want to take the derivative of this with respect to time as they're changing. So A is just going to be dA dt. When we take the derivative of this, they're being multiplied, so we have to do the product rule. L is going to stay. Derivative of W is 1 dW dt. Plus the derivative, or keep W, derivative of L is dL dt. And now we plug in everything we know. We're trying to figure out how the area is changing, so this is what we want to know. They tell us the length is 4 inches, and the width is growing by 6 inches per second. The width is 2 inches, and the length is growing by 9 inches per second. This is 24 plus 18, which is 30 plus 12, 42. All right, and then area, so it's inches squared per second. All right, so this one, pretty straightforward. You know the area formula. You just take your derivatives with respect to time. Remember, whenever you take the derivative of a variable, you get that d variable dt, and then plugging in the information you know. All right, a right triangle has legs. The short leg is decreasing. The long leg is growing. What is the rate of change of the hypotenuse? So we have a triangle. We have two sides. Let's call them A and B. And the hypotenuse we'll call H. All right, so we need to relate H to A and B. The way we relate sides of a right triangle is the Pythagorean theorem. This one's very common for related rates. This one's actually nice. Taking the derivative is not too bad. We're going to get 2H dH dt equals 2A dA dt plus 2B dB dt. We don't know H in the problem. It's not given to us, but, all right, so let's just say this. We're trying to find this. We're trying to figure out how the hypotenuse is changing, but we don't know the actual hypotenuse, but we can find it using our original Pythagorean theorem, the original hypotenuse at the time. We know our side lengths. What is 16 squared? That one I don't have memorized. 256, that's my guess. It is 256. We add those two together. We have 400. Take the square roots, H is 20. Right, so at this exact moment, when these are the sides of my right triangle, the hypotenuse is 20. All right, we know the side length. It says the short leg and the long leg. So the short leg is 12. We'll put that first. And the short leg is decreasing by 10. So we're going to put a minus 10 because that side is getting smaller. the long leg is 16, and the long leg is growing by 3. All right, so now we're trying to solve this equation for dH dt. So we're going to kind of simplify this right-hand side. 2 times 12 times 10 is negative 240 plus 2 times 16 times 3 is 96. It's negative 144. Divide by 40 to get dH dt all by itself. And that simplifies to, oh my goodness, 18 over 5. All right, and this is just a distance, so it's going to be inches per second. All right, so this one, whenever you're talking about the hypotenuse of a right triangle, you're always thinking about the Pythagorean theorem. Fairly simple to take the derivative, all of them the same. The 2 comes down, and you have the dH dt. All right, this one requires a little bit of extra work. They don't give you how long the hypotenuse is, but at this exact moment, when the side lengths are 12 and 16, you can use the Pythagorean theorem to figure out the hypotenuse is 20. Everything else, you're basically just plugging in the information that's given to you. Only extra difficulty, remember, decreasing means your rate is negative, and then plug everything in and simplify. So even though this side's going down or growing very small, and this side is decreasing pretty quickly, right now they are getting farther apart. Oh no, this should be negative. The distance actually is shrinking. And our last problem is like the full word problem where you have to read it, figure out what's going on. And there it is. Okay. All right, so here we have a rocket being launched and it rises vertically. So let's just draw a little picture, a little launch pad and a rocket. All right, so the rocket's going up. We have a camera positioned 5,000 feet from the launch pad. So we have this little like camera here. When the rocket is 1,000 feet above the launch pad, all right, so let's make it 1,000 feet above the launch pad. Oh, also this distance here we know is 5,000 feet. Its velocity is 6,000 feet per second, so it's going up at 600 feet per second. Find the necessary rate of change of the camera's angle as a function of time. So the angle of the camera as it's looking up at that. Right. All right, so how can we do this? Well, we're trying to figure out some formula for the angle. All right. And if we're doing something with an angle, and you can tell right here it's a triangle, we're going to do SOHCAHTOA. So in this case, we have tangent of this angle theta is TOA 1,000 over 5,000. Oh no, that's not right. These are changing values, so we're going to say the height over 5,000. Why can I plug in a height here, but 5,000 here? This distance is not changing throughout the whole problem, so it's a constant, so it can stay in the original problem. H, on the other hand, is changing as this thing goes up and down, so H has to be a variable. All right, so now we can take derivatives. Tangent of theta turns into secant squared theta d theta dt. The derivative of H over 5,000 is just 1 over 5,000, right? Just H turns into 1. All right, so now we plug in what we know. Secant squared of theta. Secant is 1 over cosine. Cosine is ca, so it's H over A. So we need to figure out H and A for this angle. So we don't know H yet, so let's figure that out. H squared equals 5,000 squared plus 1,000 squared. I'm just going to let the calculator do the whole thing. So the square root of 5,000 squared plus 1,000 squared is 5099.020. All right, rounding to 3 decimal places, that's what you normally do in calc. All right, so secant is that hypotenuse over the adjacent side, 5,000, squared d theta dt equals 1 over 5,000. All right, this I'm also just going to put in a calculator, so I'm going to do that, divided by 5,000, and then square all that. Did I just square it? you get 1.04. d theta dt is 1 over 5,000. And I just divide by 1.04. So 1 divided by 5,000. And divided by 1.04. I get And it's just funny because in calc, we can just go to 3 decimal places. So actually the answer would be like 0 if you went to 3 decimal places. But if you go out far enough, you get the small amount of radians per second. So as this thing's radiating the camera, it actually doesn't have to move super fast to keep it in focus at this exact moment. Also notice it didn't really matter how fast oh, I forgot a part of it. That's why. I was about to say, it doesn't matter how fast it's going, but it should. What do I have to fix? Took the derivative of h, I should have a dh dt. So this should be a dh dt. This should be a 600. I divided this. So basically, I just have to multiply this answer by 600 to get the right answer. All right, that makes it a little bit more sense. It's a little bit bigger number, not a huge number, but it's not 0. 0.1153 radians per second. All right, so I even forgot to do this little chain rule part. Took the derivative of h. It seems simple, it just turns to 1, but I took the derivative of h with respect to time, so I need that dh dt in the whole thing. All right, so I made a mistake, but you can see my mistake now, so you don't forget it as well. All right, so that's the full Unit 6 practice test. All right, so now you can go through that and make sure you know how to do all those problems. Of course, everything's gonna be a little bit different, especially this word problem. And the word problem's definitely not gonna be the exact same one, so just be ready for different types of word problems we've seen, Pythagorean theorem type ones, ones with rectangles, all that type of stuff, some SOHCAHTOA ones. Just be prepared for those because you never really know what type of word problem you're gonna get. But everything else, a lot of flashcard stuff for remembering your trig derivatives and antiderivatives, but pretty much everything you've seen before on a different test, but now there's just that trigonometry component added to it.